time flew by, I would say, and I apologize for having to disrupt all your conversations right now at the booth. I can see you still ongoing, but please all take your seats. So, I would like to welcome with us Naresh Nayak from Bosch, who will also present us sort of an idea or reusability of a certain concept for the automotive industry, and I understand that's also part of his job in general to look at these things. So reimagining vehicular communication using programmable data plane technology. So welcome Naresh, sorry.
So, hello everyone, and I would like to begin by thanking the organizing committee for organizing such a nice event. This is my first time here and has been an extreme pleasure. I'll begin with a short introduction because I'm relatively new here. My name is Naresh, and along with my colleagues at Bosch Research, I've been presenting this talk. Among the many things that we do at Bosch Research, one of the things is looking at new technologies in other networking domains which are creating a buzz, and try to derive the implications for automotive networks. And in this talk, basically, we'll be describing some of our experiences with programmable data plane technologies, which are currently a hype topic in data center networking. Yeah, so the agenda of my talk is as follows. I begin with a brief motivation of why we need programmability or flexibility in vehicular networks, and give a brief overview of programmable data plane technologies before going on to some of the use cases that we have tried to solve using these technologies. So this is a car of the future, and if we now in general ask, depending upon whom you ask, what are the requirements of such a vehicle of the future, some would directly begin automated driving or teleoperated driving, something like you see in automated valet parking. And one of the requirements in such autonomous systems is strong fault tolerance. So there has to be a certain degree of redundance, and when something fails, the EE architecture has to be reconfigured rather quickly so that the redundant components can act, and the vehicle is in a safe state, so something like a fail-safe state or even a fail operational state. Others would also treat vehicles of the future as smartphone on wheels, which means you can install applications which require data which perhaps didn't even exist or was not even accounted when these EE architectures were designed. So basically what we need to do is future-proof our EE architectures, and I would like to draw the attention to yesterday's keynote, where one of the challenges mentioned by Graham was also design for upgradability. And now if we think, what do we need for future-proofing EE architectures? So the first thing is we need bandwidth, and we need lots of it. I think in this circle or in this community, the standardization activities towards multi-gig Ethernet is already going on. So I think here the industry is on a good trajectory. What we need beyond that is freedom from interference. And yesterday's talk was, yesterday we had quite a few talks which described tens of TSN shapers which can be combined in, I don't know, hundreds of ways with different priority mechanisms. And I guess there is a solution for different use cases basically here. What we need after that is the ability of adapting the EE architecture to the changing communication patterns and do that in the field. And here I think the concepts are in a rather nascent stage, and here there's scope for different technologies that have already made their mark in something like data center networking to play a role. So whenever we speak about flexible or programmable networking, one thing that always gets mentioned is software-defined networking, and we already had a talk from Christian in the previous session where he described how the software-defined networking concept can be implemented in an automotive EE architecture. Now, how this concept basically works is you separate the network control plane from the data plane, and you have something like a centralized SDN controller, or some may also call it as the vehicle network controller. And this controller is basically observing the different events that's happening in the EE architecture, so the different traffic patterns. And based on that, it creates a global view of what's happening in the network and tries to configure the network in a way that all the applications can receive their fair share of networking resources. Now, SDN comes from data center networking, and they very soon noted a problem there. I mean, the way SDN works is you have a centralized controller which regularly interacts with the network elements like switches. It polls different counters and registers, creates this global view, and then programs the switches, which is usually, again, writing of some registers or writing into some TCAM entries. The problem here is there's only so much the SDN controller can do, because the processing of packets that happens in the network elements is baked in silicon. So the SDN controller cannot magically make a switch process the packets in some other way in which the switch was not designed to process packets. And this is exactly where programmable data plane technologies come into picture. Right now, if you want to do something, process the packets in some other way, the only way remains is to go to the CPU of the switch, which is then painfully slow and doesn't scale, or you need to include special hardware for it. So programmable data plane technologies have now been introduced in data center networking for quite some time, and they have basically two aspects. So the first one is a meta model of how the data plane processes the packets, and that's what you see in this slide here. So the processing pipeline for packets starts with a programmable parser. So a packet that comes in is parsed by this programmable parser, which is implemented as a state machine, and the header fields of interest are extracted. And the set of header fields are then processed one after the other by a sequence of match action tables. So this match action tables basically match on these header fields of interest in arbitrary combinations, and can also use some kind of metadata for matching. And if in an event of a positive match, certain custom actions can be executed on these header fields. And finally, at the end of this pipeline, the header fields are put together, the packet is reconstructed, and the packet is sent to the egress port. Now, here in this slide, you see the second aspect of programmable data plane technology. So once you have this meta model, the second thing is to describe how your forwarding function looks like. And for that, there are different network modeling languages. Here I've taken an example of one of the more popular languages called P4. That's also quite popular in data center networking. And this program basically describes IPv4 forwarding. It starts with a couple of includes, usual in programming languages, and then on the left side, bottom, you see the programmable parser. So it's a state machine which extracts the Ethernet and IP header fields. In the central column, you see the description of how the lookup tables are modeled. So here it's longest prefix matching for IPv4 destination addresses. Finally, you have some custom actions defined, like drop or forward the packet on a certain port. And finally, you have on the right side the deparser, which reconstructs the packets out of these header fields. So this is a simple description of how the forwarding pipeline is going to process your packets for a simple function. Yeah. So future proofing is where I started with. SDN brings what we call as control plane programmability, which means how your control plane of the network is. You can define it using software. And data plane programmability is a little going into the hardware side. So you describe how the packet has to be processed in the hardware. Together, these two technologies can give you fully programmable networks. That being said, this technology, this programmable data plane is not coupled with SDN. This can also be used in a non-SDN architecture, just like the normal switches. Yeah. So these programmable data planes, there are quite a few products that are already available in the market. Being data center switches, these are provisioned for high throughput. The ones that we have played with have a total throughput of 6.5 terabits per second. In the meanwhile, I think more than the double of this throughput is available also in the market. Being provisioned for high throughput also means they have very few real-time considerations. So the question that we posed ourselves was, how can we bring this really this kind of programmable technologies into automotive switches? Now moving towards TSN, which has completely different requirements, is now setting service-oriented communication as a base for it. And in the next few slides, I'll present some of the use cases, but there we have really gone in with the idea, take this technology as a treat this technology as a hammer, and then look for possible nails. Yeah. So service-oriented communication in automotive. I guess there were quite a few talks on this topic yesterday. The idea here is the future software, automotive software, will be developed as a loose collection of services, and these services will at runtime discover each other and then communicate with appropriate services to realize some kind of distributed applications. And there are quite a few service-oriented communication middlewares in discussion. Some IP, DDS is the ones that we get to hear often. And what we have observed is these middlewares usually are designed for an IP overlay network. So it's agnostic basically to the underlying network topology. The discovery sometimes, the middleware is completely distributed in the end systems or the end ECUs, and the discovery mechanisms really don't care about how the network is constructed. And on the other hand, the network is forwarding packets or IP packets or Ethernet frames. They really don't realize the frames that they are transporting have something to do with these services. So the question is, if we have this programmable data plane technologies, can we do something better for service-oriented communication? And if you look in literature, these technologies have been quite useful for bringing some kind of application awareness into the underlying switches or underlying network. So basically, the network then realizes it's transporting services, and that way can be much more efficient when it comes to forwarding. So in the next few slides, basically we tried out some use cases from service-oriented communication. We took some IP and DDS as reference and tried to implement different scenarios. So first one was runtime service discovery. And as I mentioned, because the service-oriented communication middlewares, they are completely distributed in the end systems. It's rather inefficient when it comes to distribution of this service discovery information. Usually it's done using UDP multicasts. And in middlewares like DDS, there's the scalability issue, which means the discovery overhead scales quadratically to the number of participants in the network. So with every increasing participant, the amount of discovery overhead that increases over proportionally. Yeah. And once I mean, all the participants basically get information about all the services and the deployment in the network. And with this information, then they start subscribing or publishing information to the services as necessary. So what happens here is, what you see in this slide is we have 4 services, and only the service S4 is interested in information from service S1. However, because of this UDP multicast, all the services get to know the information about all the other services, which is at times inefficient. If we can offload parts of the service-oriented communication middleware into the switches using these programmable data plane technologies, the switches can really figure out at line rate, when they are processing the packets, which services are requesting for which other services, and in this multicast tree can be pruned and service discovery can be made much efficient. And this can also be extended towards data delivery. So if there is a broadcast of data that's happening between services, the network can really detect which services really need this information and prune the multicast tree so that only the interested services get this data. What we can also do with once we have offloaded parts of this communication middleware into the switches, you can also do something like a centralized discovery, which means if there is a centralized network controller that can help match services better, because you can have redundant services in the network, and which services should talk to which service, which other services can be better decided by a centralized controller using its global view, basically. What we can also do is some kind of a hybrid combination of this centralized or decentralized service discovery. Our next use case goes into a little bit of fault tolerance. What I try to motivate in the very first slide. And here we talk about application layer fault tolerance. So if we have, for instance, multiple talkers delivering data to a particular application, what we can do is we can program the underlying network that the services delivering data, they are redundant, and the network takes care that only one copy is delivered to the end subscriber. In an event of failure, the switch detects the failure of the service automatically, because it sees, hey, there is no message, or there's no heartbeat, or there's no communication coming from a certain port, and can very quickly switch to the secondary service or secondary sensor. This basically gives faster failover times, because now the failures don't need to be detected in the application layer. because it's happening directly in the network. This results in orders of magnitude better performance when it comes to failover times. And this could be maybe the decisive factor in autonomous vehicles, where the use case is basically faster failover times. We have some evaluations with real hardware for this particular scenario, which we have published at IFIP Networking. In the slide, there's a link for it. Yeah. Now, one of the more crazy ideas that we have tried to implement using this programmable data plane technologies is application-specific computing. So we have something like a control loop where we have sensor data that's being processed by a control algorithm to steer some actuators. Usually this is implemented in ECU. And because we have this programmable data plane where we have a pipeline that we can program, we tried to push this control algorithm to be implemented in the switch. So basically the sensor stream that's coming, that's processed at line rate by the switch. And based on certain set points that's programmed by an ECU, the actuator can be steered. This basically gives better control over the latency, because you now avoid the path from the switch to the ECU, and yeah, better quality of control. The ECU is also relieved because now there's one less process to handle, and what the ECU can basically do is just change the set points, or it just needs to be active in an event of error control, basically. Yeah. Now I come to some of the open questions or challenges when it comes to this programmable data plane technologies. I mean, this technology was really designed for data center networking. And accordingly, the tooling that comes, it's handled, it doesn't have any safety considerations, or is not certified for safety critical functions. The other problem that we have in this technology is encryption, because the way application logic is offloaded into these switches is by encoding them into some kind of header fields, which can be extracted and interpreted by the switch. Now, if these header fields are encrypted, there's very little that the switches can do here. The other question is how to handle the interplay with TSN. The technology itself deals with forwarding and not with scheduling of when a packet will go out of the egress port. So in that way, it's orthogonal to the different TSN shapers that are available. But the question is, yeah, how could we define now also in these modeling languages what kind of traffic gets what kind of shapers? Finally, standards. I guess in this industry, standardization is the main goal. So if there is a chance that some aspects of this technology comes into automotive, it needs to be discussed in this community, in this group of people, and that's precisely why we thought it's a good idea to present our work here. Yeah, so now I'll conclude with a short outlook. So programmable data plane technologies as a networking technology has been a game changer in data centers. It has given access for developers directly into the switching ASIC, and that way increase the speed of innovation, because by avoiding these iterations with the switching vendors, it has enabled application developers to offload parts of their application into the hardware and thus benefit from customized hardware accelerators. the technology doesn't cover all the requirements when it comes to automotive. I guess there are plenty of open challenges, and the reason for being here and presenting this is just to give to this community, hey, there's also nice work happening somewhere outside, which could be useful for the automotive industry in general. With this, I would like to conclude my talk. I can take questions. If we got you curious, here are our contact details. You can get in touch.
Okay, thank you very much. So online takes a little longer, I heard. 20 seconds about delay before anybody online actually, before this talks concludes. So we can go into the future. You already said it in your slides, but maybe you can reiterate it. How does it interact or interrelate with everything that's done in TSN?
So TSN, I would say, is TSN brings set of standards which goes into scheduling of when a particular frame goes out. It looks into some kind of ingress policing, the rate at which packets come in. And here, this technology basically is about when a packet comes in, how is it supposed to be processed. In that way, I think it's a complementary technology to TSN. This technology doesn't define how the scheduling of packet processing is to be done. That's where maybe there's a good chance of bringing these two worlds together.
Okay, thank you. Okay, there is a question. Okay.
2 online questions. The first is from David Fox, who asks, how will the switch route some IP packets? This route is based on layer 5. So I think the first part is the question. How will the switch route some IP packets, is his question.
Yeah, so the thing that this technology brings is the programmable parser. So you can describe how your packet looks like in this parser, and then you can parse up to, I mean, the boundary between these different layers, they start blurring, because now you can parse as much as your hardware allows. So basically you can parse up to what you now call as layer 5. And once you have this data, you can do the forwarding based on this some IP service ID instead of doing it on the basis of IP address, for instance.
Okay, I hope that answers David's question. And then we have a question from Harry Palmer again. And can PDP be linked or work together with the Yang models?
That's a good question. I guess yes, because Yang and the scope of Yang and scope of these network modeling languages are different. Yang basically is used for describing the different so the register configurations, or what basically this device brings in, that's being modeled. And with this network modeling languages, you are modeling how a packet is being processed. So I think they two can be combined.
Okay, that's all the questions I had right now.
Okay, then I'm not seeing any more questions. Then thank you very much once more for the presentation.